we talked about last time. Specifically, as Megan mentioned in the middle of class, the detection of gravitational waves. In the scientific community, it's very big news. And in my research area, which is black holes and the Big Bang Theory and stuff, it is very big, very, very big news. So we'll try to talk a little bit about that today. Okay, supplemental instruction, schedule, normal schedule this week. And by the way, I put in case you want to make a note, I set up a new page called SIHQ. And it is linked to the home page for this course in Web Courses. And what it has is a link to the Thursday session. It has this same schedule. And then it has a link to the Thursday session that you'll use every Thursday. And then it has a list also of the recordings of the Thursday sessions, the last 3 sessions anyways. So hopefully you'll be able to take advantage of that to either participate in the Thursday session or at least get to the recording of the Thursday session. By the way, the Thursday session ought to be the best one to go to in the week because you're able to really tackle stuff for Tuesday and Thursday lecture. And of course, Monday would have the same effect because it helps you do homework that's due on Tuesday. Did we have homework? Yes, we did. We had homework this weekend. So actually, all these things are really good. All right, let's talk about gravitational wave news. I'm going to compare gravitational waves and electromagnetic waves. Now, we're going to learn about electromagnetic waves in a few weeks. For now, let's just make a note that the source of electromagnetic radiation, the most elementary source, is not an electric charge per se. It is an accelerating electric charge. So electric charges, either protons or electrons, usually. And a good example of that is a big radio tower. Now, this is a radio tower up in Atlanta. I just, Googled radio antenna, radio station antenna, and this was one of the nicest pictures. Now, electromagnetic radiation, our eyes are adapted for that. In fact, your eyes are extremely sensitive to electromagnetic radiation in the visible wavelengths, from red to orange, yellow, green, blue, indigo, and violet. But we are not that sensitive to ultraviolet and X-rays. Your skin is, your skin will, but not your eyes. We're not that sensitive the other direction, infrared, microwave, radio wavelengths, in your eye anyways. But those are electromagnetic waves. Now, gravitational waves are different. And this is a pair of images here from an article from a YouTube that is embedded in an article from Science Magazine, which is one of the premier research journals of the United States. And those are 2 instances in kind of a cool animation of gravitational waves. Gravitational waves, they don't look like waves in the ocean because they act on 2 different axes. They're squeezing in along one axis and then they're expanding outward on another axis, perpendicular to that. So they look, you got to see this video to really see it in action, but it looks kind of like an amoeba kind of floating down a river or something. I don't know, it's weird. But the source of gravitational radiation is very similar. And we looked at the law of universal gravitation last time, G times m1 times m2 over r squared. The electromagnetic interaction will look very, very similar. The source of gravitational radiation is very similar as well. gravitational masses that accelerate. For instance, the Earth orbiting the Sun emits very weak or causes very weak gravitational radiation or gravitational waves to radiate outwards. What they discovered last week was a very strong source from two large black holes. And the black holes that were interacting and that they saw them in their last half orbit before they merged together to form one big black hole. Those two black holes, the small one was 29 times the mass of the Sun. And the bigger one was 36 times the mass of the Sun, plus or minus a few masses of the Sun. So to within, about plus or minus 4 times the mass of the Sun. Those are the masses of the objects that we saw in less than a second merge into one big black hole. And it was 1.3 billion light years away. So it's very distant. But it was incredibly violent. And because of that, we were able to pick up these amoeba waves from 1.3 billion light years distance. Now, the reason that gravitational waves are hard to detect, and this, you know what, guys, this should actually be number 3, because this is the same outline. Gravity is very, very much weaker than electromagnetism. And if you measure two objects that interact electromagnetically and gravitationally, you can compare the size of the forces. So a proton and an electron that are bound together electromagnetically in an atom, they have a certain distance that they're apart. And because each has a mass, they also have a gravitational interaction. And the gravitational interaction is extremely weak. So if you say that, for instance, in your hypothetical or average hydrogen atom, that the gravitational force between a proton and electron in that hydrogen atom is exactly 1 unit of force, then the simultaneous electromagnetic interaction force is this big. And that is a 1 followed by 40 zeros. And matter of fact, let me see if I can count them here. I think it's supposed to be 40 zeros. Let's see. Okay, there's 1 here, 4, 7, 10, 13, 16, 19, 22, 25, 28, 31, 34, 37, 40. So write a 10, a comma, and then just keep writing zeros and commas until you get to this number. And that is how many times the electromagnetic interaction is for two objects that are the same distance apart. That's how many times stronger it is. And because that is the case, it is much easier for us to observe electromagnetic radiation. So instead of going all googly-eyed about how big the electromagnetic radiation is, just appreciate the fact that that we actually were able to observe gravitational waves. They're very weak, but if your source is really, really bright, yeah, you can see it. And theoretically, you can see it. And we've been working hard the past 20 years or so to do that. And the machine that they have is a machine called LIGO. It's actually a pair of machines. And you can read about them in the journal Science that I mentioned, a link for which I have placed in a new web page in our web courses area. It's called Extra Readings, and I'll be putting up other stuff in there, but I thought this was a good place to start. a little blurb about LIGO. These two detectors, which you can look at in the article that I posted, there's a video, actually the video of the two blue amoeba waves going through there. That same video has a few action shots of the two big detectors. One of them is in Hanford, Washington, which is out on the Columbia Plateau in western Washington state. And the other one is in Livingston, Indiana, which is down in the wetlands area of Louisiana. And so they put these big detectors there, and the two detectors talk to each other. And the detectors, they can detect the pounding of surf in the ocean easily 200 miles away. And we can't even hear it from Cocoa Beach 30 miles away. But these machines, they're like, in a way, they're like a seismograph. You know, a seismograph is something that observes oscillations in the earth itself that we call earthquakes. And this LIGO device uses lasers. They could easily use it to be incredibly sensitive detector of earthquakes. But what they want it for is detecting these really teeny tiny minuscule gravitational waves. And so they filter out all the background noise that they can. You know, when you're here in the lecture hall and you're trying to pay attention to me blabbing my mouth up here, you have to filter out, you know, whatever your seat, you know, somebody sitting next to you, you know, maybe they're goofing around on Facebook or Yik Yak or something. And see, I see some guy in the back smiling. Yeah, that actually is what I'm doing, Dr. B. So, but anyways, so you got to filter out a lot of stuff. You got to filter out background noise. You do it normally. You don't. Even little babies do it. Because whenever you focus and concentrate on something, just think of all the stuff that you're not paying attention to. It's amazing when you think about it. And that's what these detectors have been able to do. So they filter out earthquakes. They filter out guys having their lunch, you know, in the control room. I mean, they filter out as much as they can of all the sources of gravitational rattling. And when they do that, they get a signal like this. This is September, I think it was September 14th, 2015, at about 5:50 a.m. Orlando time. So I was up and drinking coffee and watching the news, Channel 9 Eyewitness News, when this came through. Now here's what they got. And this is a real research article. This is the real thing. So this is not some baby-sized version. You know, this is the real thing. My colleagues looked at this data very carefully. All right, so here's the signal coming in. Now look at this rattle here. This is the red one. This is for the detector out in Washington State. Just kind of between a little bit south of Seattle, a little bit north of Portland, Oregon. And here's the big rattle. Now here's the same over here at the machine down in Livingston, Louisiana. And they filtered out all this stuff. And this blue curve here shows Livingston, Louisiana. Now what they did in this picture, they took this red one from Hanford and they flipped it upside down. And then they shifted it forward in time because apparently the signal came first here, and then 7 milliseconds later it came to Livingston, Louisiana. Because the light travel time it's not very long, 7 milliseconds, but they can measure it. They're 1,000 miles or more away from each other. And so when they saw this, they said, "Uh-oh, we got something." And they knew that it was not the surf out in the Pacific. It wasn't the surf down the Gulf of Mexico, down Atchafalaya River, Atchafalaya Bay. They knew it wasn't some guy driving by in his dump truck 40 miles away in Livingston, Louisiana. They knew it wasn't some guy dropping his lunchbox, in the control room, or some guy tripping over his own feet. They knew it wasn't any of that. And here's why they knew. These curves down here, these are the theoretical curves. Now, I've never generated one of these things, but I know how to do it. The same thing that I do with my research, the guys do to figure out these gravitational waves. So they said, all right, if we have a pair of black holes about 29 and 36 times the mass of the sun, and the last half lap that they go through orbiting each other before they combine, you're going to get gravitational waves that look like this when they go through a detector, like the ones that we have built. And so they matched them up to these theoretical curves, and they said, by God, that's exactly what we got. So they took all their waveforms, and so they have a gallery of waveforms. They have 20 and 21, 20 and 22, 20 and 23 times the mass of the sun, 20 and 24 times the mass of the sun, 20 times the mass of the sun, 25 times the... And when they got to 29 and 36, they said, that's it. And that's what this is down here. Now this line down here, they subtracted the observations at the top from the theoretical curve of 29 and 36, and this is the leftovers. It's what they call the residual. And it's pretty even. That looks like static. That is background noise. Okay, so that's like the surf, a little bit of surf, or maybe some guy in New York City sneezing, or whatever it happens to be. This is the background noise. And they filtered that stuff out, and they got it. That is two black holes bigger than the sun, or more mass than the sun, squeezed down into radii less than 200 kilometers. So the distance from here to Tampa, just imagine two things a couple dozen times the mass of the sun that close together and orbiting each other in less than a second. And then forming one big black hole when they break through. And when they break through, they emit this enormous burst of gravitational radiation. It's it's a wrinkle in space-time that just propagates outward like waves, a little bit like waves in a pond. And this is what it looks like. As I said, there's a cool video posted in web courses on the so make a note of it, extra readings page in web courses. There's a cool video, and there's a good article that you guys can read. It's a news article, not the technical article, but a news article about it, and you can read that one as well, and I encourage you to do that because there's a lot to learn. I want you to underline the word interactions because that is what we're going to start talking about. And we're going to talk about stuff like how an astronaut, when he's working out on the space station, and he's trying to muscle something and put it in place, how does he interact with that piece of space equipment? Because out there, he's not anchored to the floor, May, the way we are, because we have gravity here. Up there, he's in free fall, so he doesn't feel like he has any gravity. Everything's falling at the same time, at the same rate, so nobody's accelerating relative to each other unless you push on something. All right, so this is what we're going to start talking about. If you think about an astronaut and a spacecraft, a little tiny spacecraft in this case, pushing off from each other. You can actually think about it the way we thought about two skateboarders that push off from each other. Sava and who was the other skateboarder? I can't remember who the other Anyways, the two skateboarders that we had up here. One thing you can say about them, they're in contact for the same amount of time. And because of the third law, their interaction forces are the same size, although they're opposite directions. So the product, F delta T, has got to be equal for each of them. Because delta T, the interaction time, is the same, because that's the contact time. And then third law interaction forces are the same. You know, whatever it happens to be, 500 and 500 the opposite way. Those are the same. So the product has got to be the same, whatever it is. Now, I've symbolized that in this formula. All right? Force of the human on the spacecraft times the interaction time is equal to the force of the spacecraft on the human times the interaction time, except for this minus sign here. Now, what that means is it's in the opposite direction. So the force on the human is in the opposite direction than the force on the spacecraft. But other than that, in terms of magnitude, you know, the number of newtons, the number of seconds, yes, they're the same size. All right? Now, this is a result of Newton's third law and just the definition of contact. Newton's second law allows us to state this right here, that the force on the human is equal to the human's mass times the acceleration of the human. In other words, second law says F equals ma. All right? So let's break it down over here. The force on the spacecraft is equal to the mass of the spacecraft, m subscript s, times whatever acceleration it gets. Now, it might not be the same, just like the two skateboarders. They didn't have identical accelerations. They didn't have identical velocity states. But what they did have that was equal was F delta T. Okay? And so here's that expression. Now let me point out one more thing about this. Let's use the definition of acceleration. Right here, A subscript H, by definition, is delta V over delta T. And now look what you've got. You can actually cancel out now delta T's here on this side, and you can cancel out delta T over here, because the acceleration only occurs when you're pushing off, when you're interacting. All right? So the delta T in the numerator here and the delta T in the denominator here are the same, Alexis. Okay? And so effectively, you can cancel them out. And when you do that, you are left with a quantity m times delta V for each individual. The mass of the human times delta V of the human, the mass of the spacecraft times delta V of the spacecraft. And those will be equal but opposite. Question? It is. That is correct. There should be, yep, thank you. There should be a minus sign here. Thank you. Right here. I'll have to add that in for the next, and in fact, I've got it right here. Right, so this is the way it should read. Okay, now, after you cancel out those delta T's, you have this quantity, m delta V. If you define as guys from the days of Sir Isaac Newton onward, if you define the concept of momentum in this way, the mass times the velocity, or mass times the speed, then this quantity here, m delta v, is equal to the change in the momentum. All right, so delta p is equal to m delta v. So here's the scalar version, and here's the vector version. It's based on the changes of two velocities. Now that's the two velocities, v1 and v2 for the human, and then v1 and v2 for the spacecraft. So don't get them mixed up. Okay. But yeah, so V initial and V final for the spacecraft. V initial, V final for the human, for the space, for this space cadet up here, whoever it happens to be. Looks like he needs a haircut. All right. Now, mass being a scalar is a constant for this particular system. And so another way to describe this result of the third law, the second law, and the definition of acceleration is simply to say this, that the momentum exchange between the human astronaut and the spacecraft are equal but opposite. And this is the quantity that is really the equal thing in Newton's third law. The momentum. The momentum exchange between the two objects is equal but opposite. Or you could, stick to Newton's third law, the way we normally think about it, is perfectly fine. There's no doubt about that. But the quantity momentum is something called a dynamical variable. And it fits into Einstein's theory of relativity, his four-dimensional view of space-time, perfectly, in a way that forces do not. And so momentum, this concept that we've defined in terms, starting with the third law, the second law, and the definition of acceleration, we've gotten to this concept of momentum, P equals mv, that is actually the best and most useful way for defining interaction of objects. And then the thing that goes along with momentum is energy, and we'll be defining that probably starting on Thursday this week, energy. But for right now, momentum. So you could say this, that, as I said, that the momentum of the human, the change in his momentum, is equal but opposite to, in other words, the minus sign, the change in momentum of the spacecraft. All right? And that is the thing that is equal between the two objects. The velocities are not, because the masses might not be. But no matter what the masses and velocities are, the MVs change by the same amount for human and spacecraft, for Carl and Bob, the skateboarders. And now you can read the rest of the introduction of Chapter 4, all about that momentum or that accounting for the change in the states of motion of Carl and Bob when they pushed off each other. You can now read the right-hand column of that example, the interaction, the momentum interaction column. Let me pause for a question. Or if something cool just came in over the news feed. Question? Mass, MH here is the mass of the human. So the normal symbol is M for mass, P for momentum. P. All right. I don't know why they use the letter P, but that's what they. Because I mean, it doesn't match up to like a German word or an Italian word or something like that. But for some reason, that's the customary symbol, P. Another question. Yes.
What's the difference between a scalar version and a full vector?
Scalar version is if you know your interactions are only left or right. You know, so like bumper cars on a track, you know. Actually, bumper cars at the circuit or at do they have bumper cars at Disney? But they have bumper cars at like where do they have bumper cars around here? At the fair. Okay, so you go to the fair, your bumper cars, that's two-dimensional, so you need the vector version. But if you're on like the baby bumper car, so you can just go forward and backward at 1 mile an hour, you don't get hurt or anything like that, then you just the scalar version is fine, you know. So let's keep going. I want to introduce one more new concept that we haven't spoken until now. It's actually in chapter 4, and that is the related dynamical quantity called impulse. F delta t, we were using it just a few minutes ago. That's called the impulse. And sometimes you see it as F times t for lazy textbook writers, but I try to make it interaction force times interaction time delta t. And that equals delta p, the change in the momentum or the momentum exchange. So the change of momentum is equal to the impulse. And hey, you guys, if you think about it, this is one more version of F equals ma. Because delta p over delta t, I mean, if you cross multiply and put this delta t in the denominator on the right side, that's the ma part of, because it's really m times delta v over delta t, and that's ma. So when you're looking at this equation here, that's F equals ma, a version of it, a version of the second law. So it's all consistent. It all works out really well. This is actually the version that NASA would use, or that you would use a similar version if you're trying to figure out black hole in spirals, like we were talking about in gravitational waves. You'd use a bunch of delta t's, really, really small delta t's, a bunch of delta x's, y's, and z's, and you'd figure out all 4 dimensions very carefully and figure out what space-time is doing. If you're sending a rocket to orbit, you got to use this form here. And the reason that you have to use that form there is because if you are sending up a rocket, the mass is not a constant. Okay? Now, we're only going to be studying systems like the motion of a baseball where the mass doesn't change. But a rocket, you know, like one of these Delta IVs that lift off from Kennedy Space Center, Celine, you know, every few weeks we get a launch out there. They lose a significant amount of mass when those rockets are burning. So the mass at liftoff is much less than the mass a second after liftoff. And the second after that, it's a significant mass loss. So M is changing for those rockets. And that makes it very difficult, but not impossible, but a little bit tricky for us. So for us, we're just going to be talking about baseballs and free fall, basketballs and stuff like that. You know, frozen chickens in free fall or out in space or something like that. Matter of fact, let's talk about this problem. And this is going to be one, this is one of our targets for the semester. We're now hitting one of our targets. The stopping time, stopping distance problem. A coin of mass 0.05 kilogram sliding across a tabletop from left to right. At initial point x1, its speed is 1.7 meters per second, for instance, rightward. Then it experiences a frictional force 0.020 newtons leftward. All right? It slows down to a stop at position x2. How much time does it take? All right, now if you think about this, you know the mass of this coin. It's 0.05 kilograms. It's a nickel. And you know its momentum initially, 0.05 kilograms times 1.7 meters per second. You know its final, what's the final momentum? 0, that's right, because it stops. So make a note of it. For the stopping time problem, stopping distance problem, the final momentum is 0 because it stopped. Okay, so V2 is 0. Vector version or scalar version, whichever you like. Now, this one, okay, this is a good one. Now, what's your name again over here? Hector. Hector, this is a good one where you just go, it's left and right. And so the scalar version is fine as long as you can use pluses and minuses appropriately. Okay. We know the Hey, wait a minute. What's the interaction force in this? Or what's the stopping force? Friction, friction. Right? So friction is the F in F delta T. We don't know what delta T is, but we do know, or we can calculate, what delta P is. Okay, so P1 and P2 give us delta P. And the force in the impulse equation is 0.020 newtons left. And in this one, Hector, yes, you better use minus signs. All right, so we're going to use negative 0.020 newtons to signify leftward. And then positive numbers for the initial rightward momentum. All right, so let's try to work out this example. Okay, and I'm going to go to calculations now, and hopefully you've all got this all written down. If you don't have it written down, go back and look at the YouTube tonight after I upload it, and you can fill in your notes. Here we go. 0.05 kilograms times 1.7, it's rightward. That's your initial momentum. Now, I'm using the number 1 to signify initial or earlier, right? I could use the letter I there if I want, but I'm going to use number 1. So that works out to positive 0.085 kilogram meter per second. And hey, you guys, there's no metric unit name for momentum. Okay, like for force, the unit name is a Newton. And let's see, what other names do we have? Well, we have meter, kilogram, and second. Let's see, Newton. There's no real unit for acceleration either. And there's none for momentum. All right, here's momentum number 2, 0, ding. That one you can just write down, without hardly even messing around. Because, it stopped. Okay, so it doesn't have a direction. It's not a plus or a minus, it's a 0. But you can write 0 kilogram meters per second, that's kosher. Now, from that, you want to calculate a delta V. All right, or excuse me, a delta P. All right, so here we go. Ching. All right, and remember, it's always later minus earlier. So P2 minus P1, and that works out to 0 minus 0.085 kilogram meters per second. So my delta P over here is negative 0.085 kilogram meters per second. All right, so that's this guy right here. Ching. How you doing? Doing all right? Good. All right, now, impulse equation. Here's the impulse equation. Let's put in what we know. All right, over here, my leftward friction force, negative 0.020 newtons. Okay, that goes over here. And my stopping time, I don't know what that is. I want to know what that is. And because I can now fill in the right-hand side of the impulse equation with a number, I can figure out what delta T is. Right? Because I got a negative 0.085 kilogram meter per second over here, which is what we just calculated. We calculated it up here. Now we plug it in. And if you look at this, actually, you know what you could do? Anybody see a simplification that you can do? What do you see? No. What do you see? No. Actually, that's good too. But even before you do any of that, what do you hate most in calculations? One of the things I hate the most. That's it. See, that's one of the things I hate the most. Cancel out negative signs. All right. So you can cancel out your minus signs, ching, and just burn them out of there. All right. And when you've done that, here's your calculation. And there's the impulse equation. You plug in your known values. Now you divide both sides by negative. So if you don't cancel, you still got to divide both sides by the force to get delta T by itself. Okay, but then you get over here on the right-hand side a negative divided by negative. That's a positive. So you get rid of that bunch of negative signs anyways, no matter when you attack it. So we're looking good here. Delta T, negative 0.085 kilogram meter per second. And then the denominator. Now notice here that I've written the force. It's a newton. It's a number of newtons. Negative 0.020 newtons. But instead of that, I wrote it as kilogram meter per second squared. Now please write that down in your notes. Because it is now very, very nice to cancel everything except one little old power of seconds in the denominator here. That's the only thing that doesn't cancel out. And then, of course, you got 0.085 divided by 0.020, numerically speaking. But the only thing you've got left is seconds in the numerator. And it works out to be 4.25 seconds. So there, my wonderful students, is your stopping time. All right, and if you want to round it off, like in the homework, I might tell you, okay, round it off to the nearest tenth. So then it'd be 4.3. All right. Now let me pause for questions because you're going to do a couple calculations now with your iClicker. Question?
So, which equation did we use at the very beginning when we were multiplying the kilograms times the meter per second?
Definition. The question was, what equation were we using at the beginning when we multiplied kilograms times meters per second? And the answer to that is we were using the definition of momentum. P equals mv. Question back here with the Black Knights t-shirt. Alexis, poke that girl behind. Yeah, did you? Yeah. Same question? Okay. Another question. Girl behind Alexis, what is your name? Yes, Rebecca. Good. I'm trying to remember names, as many as I can. Did you ever notice that some faculty they don't even bother to try? You know, I like to try. I one time memorized 200 students' names in a semester, astronomy students. So it can be done. Another question. Yes.
If it's negative or positive, it depends if it's going left or right.
The question is, if it's negative or positive, that depicts whether it's going left or right. That is correct. Negative for leftward, positive for rightward. If you want. Another question. All right, let's keep going. Let's do some impulse calculations. Okay, get your clicker out. And you should be able to get Go Nitro. You got Go Nitro? Okay, you ready? We're on frequency BB. Okay, a 4.5 kilogram blob of green jello. And the Klingon bird of prey. You know, that is a pretty cool starship. Klingon bird of prey. All right, go ahead and vote. How much impulse? How much F delta T? And of course, green jello is the best kind. Everybody knows that. You know, like the kind that your grandma, she puts little carrots and fruit cocktail in it, and then you got to eat it on Sunday because otherwise you get in trouble. Rebecca, it's great to see you kibitzing and coordinate with your seatmates there. It's good. That's why we're doing this. I love to see it. 30 seconds. Very simple question to answer. All you have to do is multiply two numbers in the impulse equation. Ding, 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 ding. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The panic is rising. The brains are melting. You ready? Are you really ready? Oh! We got some splaining to do. Because, you know, this is a tale of two cities. Look at this. There's a bunch that voted for A, and a bigger bunch that voted for D, and then a couple little subgroups, 3 subgroups for the other ones. 24 kilogram F delta T. Interaction time is 2 seconds. Interaction force, 12 newtons. F delta T. 12 times 2, 24. And that's the only 24 up there. So, you want to try another question? Let's try another. Multiple choice. Stopping time. Stopping time question for today. Now you must try. No singing?
Oh, he's doing it.
Somebody's in the back going, Dr. B, no. Okay, I'll stop singing. Stopping time. For this one, you use F delta T as well. And actually, this is like the example that we just used a few minutes ago. Na 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 na. Mm-hmm. 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 Na 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 na. 20 seconds.
Right. Oh, you're right. That's probably.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. You know what that means? Bunch of geniuses. You know, and actually, you know what it means? This means you're learning. Excellent. I got you right where I want you. All right, let's review the calculation. Here we go. Shh, shh, shh. If you got that one wrong, some of you did. A number of you did. Let's just review it for extra safety. Okay, first thing to do is figure out delta P. 0.80 times 20, that should be 0.800, not. Well, that's a weird looking, I don't know how it got like this. Forget about that 0 up there. It should be 0.800 times 22. That's 17.6. That's my change in the momentum. I've slowed down to 0 from that momentum state. All right? And my stopping force is 11 newtons. Now, I didn't really tell you the directions. You could add directions in here I've just added magnitudes, and you can sometimes get away with that if you're working on a fairly simple problem. Here's my stopping force for the basketball. And so the stopping time is simply the quotient of 17.6 kilogram meter per second divided by 11 newtons. And if you do that carefully on your calculator, you come out to 1.6. Okay, and that's what you would type in for, if you were doing it, well, that's what, if you were doing the numeric version of that problem, I would specify, to the nearest tenth of a second or to the nearest hundredth of a second. Okay, in this case, the nearest tenth. I have one more question for you. And it is not on web courses. Would you like to dismiss early? Vote A. Would you like to dismiss later? Vote B. Go ahead and vote. A for, boy, you guys are blazing here. Woo! What? Hey! Who voted for no dismissal? What a... Okay, anyways, you guys are dismissed. Homework by supper time. Homework 8. You're dismissed. I'll see you next time. 11:30. Dismissed a little bit.